Okay, this is video section 8.4. This is going to be a long one, so you've got to make sure and take notes. I will have another section of notes here that kind of sums it all up and the important pieces of it, but this is what you're going to use for your video. So our objective is we're going to graph rational functions with horizontal and vertical isotopes. We're going to graph rational functions with oblique and points of discontinuity. So let's start with what a rational function is in our vocabulary. Well, it has an equation in the form of fx. And let's go back to that and look at it. Sorry, I'm not prepared here. It's going to be in the form of f of x equal a of x over b of x, right here. Don't let this scare you. Now, a of x is just another name for saying it's some polynomial function, but we don't know what it is, so we're going to call it a of x. Or, we could have used g of x, but they just use that to tell you. And b of x is also a polynomial function. And we know, because we have a polynomial function, we're going to have variables, we have to have some limitations, because the denominator cannot be 0. So we said b of x cannot equal 0. So in order to graph rational functions, there's some key information that we need to look up. So we first start with locating the zeros and the isotopes. A zero of a function of f of x equal a of x or b of x occurs at every value for which x is undefined, or for which a of x equals 0. Sorry, the zeros. So what we're saying is we take the polynomial function, the numerator, and we equal it to 0 to find where the graph, remember zeros, roots, solutions, talked about this before, is where the graph crosses the x-axis. So we're going to take a of x and set that equal to 0. It'll make sense when we actually go through this. So let's identify what, we already said an isotope is a line that a graph approaches but never reaches. And we're going to just refresh what a vertical and a horizontal isotope. So a vertical isotope is a vertical line that a graph approaches but doesn't touch or cross. Horizontal isotope is a horizontal line that a graph approaches but doesn't touch. So it's going to be important that you write those those definitions down. And the other important thing that you need to write down is, in order to find the vertical isotope, this is why it's going to be important to know that f of x equals a of x, which just represents some polynomial function. Okay, so to find the vertical, I'm going to call it VA. You're going to take a of x and set it equal to 0 and solve for x. Okay, and those are going to be the zeros. That's where the graph is going to cross the x-axis. To find the horizontal isotope, there are 3 cases that you really need to know that are really important. Okay, so it tells you here. So the cases are: 1, there is no horizontal isotope; 2, y equals 0; 3, y equals the leading coefficient of a of x over the leading coefficient of b of x. So for a horizontal isotope, you've got 3 cases: none, the line y equals 0, or the line y equals leading coefficient of a of x divided by leading, sorry, I didn't have enough room, coefficient of b of x. Sounds like a bunch of big fancy words. It really isn't. So we'll go through this. So when is there no horizontal isotope? Okay, it's important to know. So we have to find the degrees of the 2 polynomials a of x and b of x, first of all. What is degree? Example, x squared plus 2x plus 1 is a polynomial. This has a degree of 2, 1, 0. We can go over in class if you forget what degrees are. So this entire polynomial, f of x, is going to have a degree of 2. Okay, if I have x plus 1, we'll call it g of x, it has a degree of 1, because this is 1, and constants have a degree of 0. So you're going to have a degree of 1. So you find the degree of each polynomial function first. So the degree, for case 1, if the degree of a of x is greater than the degree of b of x, that's when you have no horizontal asymptote. So you need to write that down. If you have a degree of a of x greater than b, or less than b of x, you have the case 2, y equals 0. If the degree of a of x and b of x are equal, you look at the lead coefficients, and that will be an example B if I have x squared plus 2 over 2x squared minus 3. Okay, these a of x has a degree of 2, b of x has a degree of 2, so you look at their lead coefficients, which would be these two. You take the numerator divided by the denominator, so that is the horizontal asymptote, y equals 1/2. Okay, well, we'll get more into them as we do the details, but you need to write this down. So case 1 is if the degree of a of x is greater than the degree of b of x. I'm not going to write that, you can write that. If the degree of a of x is less than the degree of b of x, and this is the degree of a of x is equal to the degree of b of x. Okay, so that is what a horizontal asymptote in the 3 cases. So let's look at an example. And here, this shows you there's no horizontal asymptote. This has 1 horizontal asymptote, so it's going to have at most 1 horizontal asymptote, never more than 1. And here has, so this one has a 2 vertical isotopes and 1 horizontal. This has 1 vertical and 1 horizontal. Okay, so this is a graph with no horizontal asymptote, and it's x cubed. Oh, goodness. Didn't mean to do that. X cubed. Find my example 1. X cubed over x minus 1. So the first thing we want to do is we want to find the zeros. So we take the numerator a of x and equal it to 0. When we solve, we get x equal 0. Okay, so we know that it's going to cross here. To find the vertical asymptote, we're going to find when it's the b of x, which is here, is undefined. So when x minus 1 equals 0, it's x equals 0. So we're going to have a vertical asymptote. Oh, sorry. X equal 1 at 1. So there is my vertical asymptote. Do I have a horizontal asymptote? So this has a degree of 3 and this has a degree of 1. Since a of x has a degree greater than the degree of b of x, there is no horizontal asymptote. So now we would make a table. So if we know this is 1, I'm going to pick 2, 1.5, -1, -2. So they go in the book and they make a chart of different values for this graph. Okay, so we're just making a chart here. So they use all these values. So when they go and plot, we know that it's going to go through 0 here. Right? So if I go and plot, say, -1, I'm going to get 0.5. If I plot -2, do you see it's going to go up higher somewhere? If I plug in -3, and I don't right now need to put the exact points. I know it's going to go up even higher. If I put, so we know it crosses, this is a 0. If I put in 0.5, I'm going to get -2.5. So my graph is doing this, and then it turns down like this. Because remember, it's an asymptote, it approaches. Now, we have the other side, so if we put in 1.5, we're going to get something like, or let's put in 1.5, and we're going to get, I don't know, 6.75. If I put in 2, I'm going to get 8. If I put in 3, I'm going to get 5, so I'm going to go up even higher. But remember, it only has 1 0, so it cannot come down. So let me just type in 1.5. Well, then I'm going to get this right here. And if I punch in 1.25 in my calculator, or I put 1.25 in the function, I'm going to get y is 7.5. So remember 1.5, y was 6.75. So at 1.5, it's about right here. 1.25, which is to the left of this, is going to be higher. So my graph is going to look like this. It's going to do some crazy thing. And if you look in the book, it does this because we know it only crosses a 0 one time. So these asymptotes are going, and zeros are going to help you graph it. So let's do another one. So sometimes in the real world, the graph of irrational functions are meaningful, and sometimes parts of them aren't. For instance, distance and number of people can never be negative. So in the contents, if this was the graph of one of those contents, then we would ignore anything to the left of 0. We would need this part over here because, again, we can't have time or distance being negative. Okay, so let's look at a real world problem. It says a boat traveled upstream r1 miles per hour. During the return trip to its original starting point, the boat traveled at r2 miles per hour. The average speed for the entire trip is given by this formula. So let r1 be the independent variable and r be the dependent variable. Draw a graph if r2 equals 10. So first of all, we're going to substitute 10 back into this graph. So we have r equals 20r1 over r1 plus 10. So the first thing we're going to do is find our zeros. So we let 20r1, which is a of x, equal to 0, and we get r1 equals 0. So it's going to cross at the origin again, at 0, 0. Okay? The vertical asymptote is when we take the denominator and equal it to 0, and it's at negative 10. So we have negative 10 right here as our vertical asymptote. We know it's going to cross at the origin. Now, what's the degree of the numerator is 1, and the degree of the denominator is 1. So our horizontal asymptote is going to be the lead coefficient divided by the lead coefficient. So it's 20 divided by 1. Y equals 20. So at 20, I have a horizontal asymptote and I have a vertical asymptote. So I know my graph's going to cross at 0, 0, and it's going to do this and this. Because remember, it has to approach the asymptote. And we can plug in points around there and verify that, and we know it's never going to cross or touch 20, and it's never going to cross or touch negative 10 on the x, vertical x equal. Okay, so what is the r-intercept? That's the same thing as saying what is the y-intercept, and we already said it's 0, 0. Okay, what domain and range values are meaningful in this context? Well, we know because we said R1 is going to be what? They said it's miles per hour, and R is the average speed. So we know they can't be negative. So we know from, this is the origin, it's hard to tell because of the graph, but the origin is right here where the 0 is. We can't go to the left of that because we can't have negative average miles per hour, and we can't go to below this because we can't have negative miles per hour, nor can we have negative average speed for a trip. All right, so the domain is going to be x greater than or equal to 0, and the range is going to be between 0 and 20. Those are the meaningful things. And that's all I was just saying. It's just graphing it and then learning what the meanings are. All right. So let's move on. So we have a couple of things. So we just did vertical and horizontal. Now we're going to touch on oblique asymptote and points of discontinuity. So an oblique asymptote, oblique means slant. So basically we have a slant asymptote, which is an oblique line, which is going to be in the form of y equals mx plus b. So how do you know if you have an oblique asymptote? Well, if the degree of a of x minus the degree of b of x equals 1, then you have an oblique asymptote at f of x equal the polynomial a of x divided by the polynomial b of x, and you disregard any remainder if there's a remainder. Okay? You also can't have no common factors other than 1, and b of x can equal 0. So let's look at an example with that in mind. Okay, so example 3 says, determine the oblique asymptote. So let's look at this equation. You're going to have f of x equals x squared plus 4x plus 4. So the first thing we want to do is we want to find the 0. So we take a of x and equal to 0 and solve. And we get x equal negative 2. So we have our graph. So 1, 2 is going to be our negative 2. Is going to be our vertical. It's going to be, no, it's going to be a 0. I lied. So ignore this. It's going to be our 0. We have to keep it straight. So we want to say, what are our roots or zeros? X equal negative 2. What is our vertical asymptote? What's our horizontal asymptote? What's our oblique asymptote? Okay, so we said the vertical asymptote is when the denominator is equal to 0. So we're going to get 2x minus 1 equals 0, 2x equal 1, x equal 1/2. So we're going to say at x equal 1/2 is going to be our vertical asymptote. And we said it's going to cross the 0, x equals negative 2. And what else do we know? Horizontal asymptote. Well, look at the degree. It's higher in the numerator than it's in the denominator, so there is no horizontal asymptote. So we say there's no horizontal asymptote. What about the oblique asymptote? Well, you have a degree of 2 and 1. 2 minus 1 is 1, so it tells me we have an oblique asymptote. We're going to take x squared plus 4x. So we're going to take x squared plus 4x plus 4. And we're going to do long division. We have to remember how to do long division. Divided by 2x minus 1. So when we go and do the division, I'm not going to do it here, you're going to get 1/2 x plus 9 over 4. And we can talk about this in class and just review this if this is important. So how do we do this? So this is what? 2.25, and this is 0.5x. Okay, so we're going to go to 1, 2, 3, so 2.25. Okay. And then we're going to keep this at 1/2. So we're going to go down 1, over 2, down 1, over 2. So basically we have a vertical asymptote at that line. So we're just graphing the y equals mx plus b equation. Okay, that's our vertical asymptote. So we know it's going to cross here. So my graph, so if I pick a point in a table, or I know that my graph is going to do something like, something like this, and it's going to do this between these two asymptotes up here. So we can plug in points if we're not sure. So we put in negative 2 into the original equation. All right, so we have negative 2, so we have 4 minus 8 is negative 4, so we have 0 divided by anything, so it's 0. And then if we put in negative 1, we get 1 minus 4 is negative 3. We get 1 over 1 is 1, so we go to 1, 1. So our graph is going to do something like this. It's going to approach this asymptote but never reach it. Okay? Now let's talk about point of discontinuity. We'll put all this together, I promise you. So the point of discontinuity is just a hole in the graph. So let's start with the example. Okay? And we'll go directly into the example. So we're looking at example 4. So it's f of x equals x squared minus 16 divided by x minus 4. So the first thing I want to do is I want to factor, and you're always going to start with this, and you're going to cancel out. So what you have left is the real graph, the graph. But this means something. Because we have common factors that cancel out, we're going to take that and set it equal to 0. We're going to x equal 4. That is going to be our hole at x equal 4, but we have to find the y because it's a coordinate. The hole is at some coordinate x comma y. So I'm going to put this in what's left here. So I'm going to do f of 4, and I'm going to get 8. So you have a hole at the coordinate 4 comma 8. But now what I have left is this graph, which means there's no oblique asymptote, no horizontal asymptote, because I no longer have the denominator. I have a hole instead. So holes trump vertical asymptotes. You would take, well, normally we would put this equal to 0, and that would be a vertical asymptote. But a hole, because you have a common factor, it cancels out with the same factor in the numerator. It's a hole. And you need to put that down. Holes trump vertical asymptotes. So now can we graph this? Yes, 1, 2, 3, 4. Yes, so we're going to go, this is going to be 1, 2, 3, 4, and 8. 8 being up here. So we know here there's going to be a hole at 4 comma 8. And I'm going to just make my line. So my line is going to do this with a hole in it. All right? So how do you have a hole? If you have any common factors, you could have more than one hole. So we're going to put all this together and do problems and have a mixture of all. So basically, learn those rules. And the first thing you're going to do is you're going to factor out any GCFs. Then you're going to find the zeros. Then you're going to find the vertical asymptote, if there is one, horizontal asymptote, if there's one, and oblique asymptote, if there's one, and then any points of discontinuity. And you're going to graph all this, and then you're going to make your graphs based on that. All right? Do the problems, and we'll see you in class.